So I'm going to prove a very helpful theorem of limits. It talks about polynomials. So we have our theorem, and I'm going to say let p of x be a polynomial, then the limit as x goes to a of p of x is simply direct substitution. It's p of a. And the proof. So recall that a polynomial p of x is always a number times x to the n plus another number times x to the n minus 1 all the way down to a number times x plus a number. Any one of these numbers could be 0. In other words, you can have 3x to the 7th plus 2x to the 6th plus 1. Oh, I meant to say like x to the 4th. In other words, we have some terms missing. We have 0x to the 6th plus 0x to the 5. And in here, we have plus or 0x cubed plus 0x squared plus 0x's. These are all zeros. They just placeholders if you wanted to insert them. But nonetheless, it's still a polynomial. And we are going to make one assumption where the first constant is not 0. If it were 0, fine. Then we'd have this polynomial, the one that starts off with a sub n plus 1. So let's assume that the first one is not 0. A(n) is not 0. Now, each of these terms, each and every one of these terms are also polynomials. But since there's one term, we call them monomial. And I am going to prove that the limit as x goes to a of any one of these arbitrary monomials, well, it's just direct substitution. So I'll call it a j x to the j. So we want this one, okay? But we know from an earlier theorem that you can pull the constant out in front. So we have aj times the limit of x raised to the j. But we know another theorem. We still have the aj in front. We have another theorem that says if you take the limit of a function to a power, you can take the limit of that function and then raise that answer to the power. So basically, if I can show that that limit is a, then I'll get a sub j times a to the j. But that's exactly what I want. I want to just replace x with a. So we just need to prove this limit in the box. And then invoke, to show that this limit is in fact a to the j. So I just want to prove that this limit is a. Okay. So first, we'll prove that the limit as x goes to a of x is simply a. Well, given any epsilon greater than 0, since I don't know that this limit is true, I have to show that there exists a delta. I must actually exhibit that delta such that when you compute the difference of x and a in absolute values, you're going to get less than epsilon whenever 0 is less than x minus a, is less than this minus that, which happens to be x minus a, which is less than delta. But this one is pretty simple. If this is less than delta, okay, so if I replace epsilon, if I say epsilon is equal to delta, then this really says x minus a is less than delta whenever the absolute value of x minus a is delta. And of course that's true. I'm just repeating myself. This here is true whenever this is true, of course. So, like I said, I need to find the delta. Oops, and to erase. Okay, so choose delta to equal epsilon. And delta is usually a function of epsilon. So choose delta equal epsilon, and this statement is always true whenever that statement is true. So now I proved it. I proved, okay, so the limit as x goes to a of aj x to the j, I can pull out the j, and instead of taking the limit of x to the j, I can just take the limit of x and raise that answer to a. Well, this is a to the j. This here we just showed is a, and I have to raise it to the j's power. So yes, I did show that the limit of this monomial is just substitution. Replace x with a, and that's just what happened. Okay, but now we know, because we proved, we know that the limit as x goes to a of f1 of x, one function, plus a second function, and so on, up to, say, an nth function. We know that that limit is equal to the limit as x goes to a of f1 of x plus the limit as x goes to a of f2 of x, all the way down to the limit as x goes to a of fn of x. Which, okay, so we know that. So now, the limit as x goes to a of p of x, this is the limit as x goes to a of whatever p of x is. And p of x is an x to the n plus an minus 1 x to the n minus 1 all the way down to a1x plus a0. But these are functions. They're not the most complicated functions, but they're functions. And like I said right up here, you can take the limits separately. So this is equal to the limit as x goes to a of anx to the n, anx to the n, plus the limit of the next one, an minus 1, x to the n minus 1, all the way down to that limit. The limit as x goes to a of a1x plus the limit of the last one. the limit as x goes to a of a sub 0. But now, we know the limit of things of this form is just direct substitution. So, the limit of the first monomial is a sub n, a to the n, plus the limit of this one is a sub n minus 1, a to the n minus 1, all the way down to the limit of that one, which is a 1 times a, plus this is just a constant, and the limit of a constant is the constant. But this last line is it's not p of x, but rather it's p of x evaluated at a. I just plugged in a for every x. That's exactly what evaluation means. So we just proved that the limit of as x goes to a of a polynomial is just p of a. The limit as x goes to a of a polynomial, and only a polynomial for now, is p of a. See you in the next proof.